Hello and welcome to Mahasri 4 Electric Zone. In today's class, we're going to understand the construction of a DC generator, one of the most important concepts in electrical machines. Did you know? The construction of a DC generator and a DC motor is almost the same. When assembling, even the technician won't know whether it's going to work as a motor or a generator. It depends on how we connect it. Let's break this topic into 5 main parts, the 5 principal components of a DC generator. 1. Field system. The field system is responsible for producing a uniform magnetic field in which the armature rotates. It includes a circular frame called the yoke pole cores and pole shoes bolted inside the yoke field coils wound on these poles. The field coils carry direct current, DC, and generate magnetic flux. Poles are arranged in such a way that adjacent poles have opposite polarity, N and S. A smaller air gap between the poles and armature, around 0.5 mm to 1.5 mm, means fewer turns are needed in the coil, making it more efficient. 2. Armature core. The armature core is mounted on the shaft and rotates between the field poles. It's made of thin, laminated soft iron sheets, 0.4 mm to 0.6 mm thick, to reduce eddy current losses, make the magnetic path efficient. The laminations are coated with insulating film so that they don't conduct between each other. 3. Armature winding. This is where the real magic happens. The armature winding is placed inside the slots of the armature core. This is where the working EMF, voltage, is actually generated. The conductors are arranged in a series parallel manner. Series connection increases voltage. Parallel paths increase current. These windings form closed loops so that current keeps flowing continuously when the generator runs. 4. Commutator. Now comes the commutator, a very crucial part. Its job is to convert the alternating EMF generated in the armature, winding into unidirectional DC voltage. It is made of copper segments, insulated from each other with mica. These segments are mounted on the shaft and rotate with the armature. Each armature conductor is connected to a commutator segment. As the shaft spins, the commutator keeps reversing connections at the right time, producing DC at the output. There are 2 common types of winding connections here: lap winding, wave winding, 5 brushes, and finally, the brushes. These are usually made of carbon and rest lightly on the rotating commutator. The purpose of the brushes is to connect the rotating commutator to the external load, transfer the generated DC voltage. If we have a 4-pole machine, we'll typically have 4 brushes, 2 brushes for the positive terminal and 2 for the negative terminal. They are placed so that brushes of the same polarity are connected together. The brushes stay still, but as the commutator rotates beneath them, the connection remains smooth, and that's how we get continuous DC output. That's it! You've now learned the complete construction of a DC generator: field system, armature core, armature, winding, commutator, brushes. This is the foundation for many other concepts in DC machines, so make sure it's crystal clear. If you found this useful, don't forget to like, share, and subscribe to Mahasri 4 Electric Zone. Let's keep making electrical engineering easy and interesting together. Welcome to Mahasri 4 Electric Zone, your Telugu guide for electrical engineering made easy. In this video, we'll learn how a DC generator generates EMF with simple explanation and diagrams. EMF generation in a simple generator. Let's understand how EMF is generated in a simple DC generator. We take a single-turn coil ABCD rotating clockwise in a uniform magnetic field, as shown in Fig. 1.1. Position 1. The coil is parallel to the magnetic flux. No flux is being cut, so the generated EMF is 0. Position 2. The coil cuts some amount of flux. A small EMF is induced, as shown at point 2 in the waveform. Position 3. The coil is at 90 degrees to the flux. It cuts the magnetic field at the maximum rate, so the induced EMF is maximum, as seen at point 3 in the sine wave. Position 4 and 5. As the coil rotates further, the EMF decreases. At position 5, the coil is again parallel to the flux, so EMF becomes 0. Position 6 to 7. Now the coil moves under a pole of opposite polarity. The EMF reverses direction and reaches maximum in reverse at point 7, position 8 and back to 1. The EMF again reduces to 0 as the cycle completes. So we observe one full sinusoidal cycle of EMF in one revolution of the coil. Why the EMF is alternating? The induced EMF in the coil is alternating in nature because the coil sides move under north and south poles alternately. But we need direct current. That's where the commutator comes in. Action of the commutator. The commutator is a metal ring split into two segments, C1 and C2, separated by mica. The coil ends AB and CD are connected to these segments. Two carbon brushes rest on these segments and collect current. Half rotation. After half a turn, the coil sides change position under opposite poles, but the commutator also rotates, reversing the connection to the brushes. The result? The current direction through the external circuit remains the same, even though the EMF in the coil is alternating. This is how the DC generator converts alternating EMF into direct voltage using the commutator. The brushes help deliver this voltage to the external load. Thank you for watching. If you found this video helpful, do give it a like, share with your classmates, and don't forget to subscribe to Mahasri 4 Electric Zone for more clear and simple engineering concepts in Telugu.